For hundreds of years, artists have used the principles of vanishing points to create realistic 3D perspective. Today we are going in the opposite direction. We will start with a perspective image and discover the vanishing points in order to understand the perspective used by the camera. This is a house. We can assume its perpendicular edges are aligned with the directions east, north, and up. There are also some diagonal lines. Although the edges are truly parallel in the real world, when that 3D scene is viewed in a 2D perspective, they appear to converge. The points at which all the lines for each direction converge are called vanishing points, and the closer lines are to appearing parallel, the further away the vanishing points are, often far beyond the edges of the image. This image has 3 vanishing points, which is what we call 3-point perspective, and any 3 points form a triangle. If we construct a perpendicular line from each side across to the opposite vertex, all 3 lines intersect, and their intersection is known as the center of the triangle. This works for any triangle. Try it. That center happens to be the principal point of the camera. Of all the light rays that fan into the camera, the principal ray is the unique ray that hits the film perpendicularly, and the principal point is where that ray hits. For a well-constructed camera, it's generally very near the center, but for a cropped image, it could be anywhere. The 3 lines that intersect at the principal point appear to be in the same flat image plane as the vanishing point triangle, separated by 120 degrees each, because all the way around is 360. But that's only because we're viewing the focal plane from directly above. If we can tilt our view to see it from the side, we can see that these lines actually define a pyramid, which is known as the perspective pyramid. The lines meet at an apex directly above the principal point. How far above? Not so far that the angles at the apex are small and pointy, not so close to the focal plane that the angles are near 120 degrees. There is a just right height at which all 3 faces are right triangles. That height is the focal length. Now that we have the focal length, that's the last piece of the puzzle, and we can assemble a mathematical model of the camera that makes projection of 3D ground coordinates into 2D pixels as easy as matrix multiplication. But that math is not the story I want to tell here. I want to help give a concrete understanding of focal length. A shorter focal length means the camera has a wide field of view. This is also known as zooming out. When shortening the focal length, parallel lines become more convergent, so vanishing points are closer in, and the base of the perspective pyramid is smaller to go with that shorter focal length. Increasing the focal length, or zooming in, narrows the field of view and makes the ground parallel lines appear closer to parallel in perspective, which pushes the vanishing points out and makes the perspective pyramid wider and taller. Here's another view of zooming in, just looking at the picture. In addition to the apparent size of the house increasing, we can see the lines getting more parallel. Imagine how those vanishing points are being pushed way further out for a larger pyramid with a taller focal length. And then zooming out, the object appears smaller, and lines that are parallel in reality appear so convergent that the house looks quite distorted. If you were zoomed out with a short focal length and the scene looks really small, you could make the house look bigger by zooming in. But another way is to just move the camera closer. However, you can see that close range combined with the short focal length results in a really distorted perspective. We can zoom in a little bit to make it look bigger, and then move out a little bit to make it smaller, and repeat in alternating steps. Zoom in, move out. Zoom in, move out. Zoom in, move out. Zoom in, move out. Or, starting from a long range and a long focal length, we could carefully decrease both focal length and range simultaneously. This is the camera effect that Alfred Hitchcock invented to express dizziness in his masterpiece Vertigo. And this is also why humanity has invented the selfie stick, because we quickly discovered that smartphone photos with close range and short focal length distort the size of your nose. I hope you enjoyed this explanation. If you want to see the Python code that made this animation, visit my GitHub page.